Yeah, Kirk, do the homework files download? I haven't been able to get them.
They should. Is everybody else getting them okay?
Yes.
Um, I forget there was.
I've noticed that the browser, it's your to download the files, it seems to be browser dependent.
Oh,
Safari didn't work for me,
okay. We
or
may.
maybe it
I
was
tried
Firefox. I'm
before
not sure.
Firefox.
I've used
Yeah,
Firefox.
Firefox didn't work.
Oh, it didn't.
Yeah, one of them didn't work. I wasn't sure if it was, but I know that Explorer did work.
Not for me.
I've been using Firefox the whole time.
Let me check something here. Works for me. You see my screen?
Yep.
So I click on it and it pops right up. Cancel. And let's see which one.
If you have your save drive set to a drive that's turned off, it'll go crazy.
Okay.
I download them all to my desktop, so that's not happening.
Okay.
Not sure what to tell you on that. We may be moving to a new website that HPSDR is going to set up. I think it'll be verilog.hpsdr.org or whatever. I'll let everybody know. That way we'll have plenty of room to put all the video files and everything. If you like, during the lecture, you can go ahead and type in questions into the chat window. I may not get to answer them. I may not see them sometimes because I get busy. But I will try and look at the chat log when we're done with the lecture and try to answer your questions if I didn't answer it during the lecture. How are we doing on time, Michael? Should we start here?
Yeah, according to my clock.
You broke up. I didn't hear you.
It's basically about time. It's okay. You can start now.
Okay, today's lecture we're going to cover a couple more things, and we're going to review a little bit of what we went through in our last lecture, because I'm going to add to it a little bit. But I'm going to last night I went through and I changed this whole slide series that I'm doing today, and I hope it's a little clearer than maybe what it was last lecture. So we want to first start talking about non-blocking assignments. Oops, I have a mouse problem again. Just a moment. Okay. So, in the simulation process we want to look at now, we're going to have a quiz here. After the next rising edge on clock, what will be the value of register A? Let's assume that we have these two always blocks, and one of them increments count, and the other sets A equal to count. And let's assume that count starts off at 42. So what will the answer be? Does anybody have any ideas? Well, if this block executes first, remember the simulation engine could pick either one. If this block executes first, count is going to be set to 43. Is that clear? And then this block will execute. And what happens to A? It's set to 43. But if this block executes first, what happens? Whoops.
Obviously, it's 42.
42. So we're going to introduce what we call non-blocking assignments so we can get away from this order dependence. So non-blocking assignment schedules a new value to be assigned at the end of the current time step. Okay? A new value is put in the assignment queue for the assigned register, and we're going to talk about this assignment queue, and we're going to talk about queues some more. Assignment takes place once all blocks have been executed during the current time step. So the syntax for this is we have a target, and then we use this less than equal for our non-blocking assignment, and then we have an expression. So let's watch what happens in this case. So let's assume that this block executes first. Okay? So currently our count is 42. It schedules a value of 43 to be assigned to count at the end of the current time step. Okay? So it schedules a value of 43. So this block executes second, and it schedules a value of 42 because so far we haven't reached the end of the current time step. We're not done yet. So it schedules a value of 42 to be placed in A. And so once all the blocks for the current time step have been executed before we advance the time, then we update our values that were scheduled. So these scheduled values now, count becomes 43 and A becomes 42. So they're order independent now. So, well, let's take a look at the other example. If this block executes first, it's still going to schedule a value of 42 right here. And if this block executes second, it's going to schedule a value of 43. And so now once all the blocks are executed, we update the scheduled assignments and we get the same results. So we're independent of execution order now. So this is very useful. And in fact, when you write RTL code, you'll be using these types of assignments and statements a lot. So after the next rising edge on clock, what will be the value of register count? Does anybody have an idea? We're going to use non-blocking here. So what happens? Anybody want to guess? Let's go through it. Let's say this block executes first. So it schedules an assignment of a value of 43 to be assigned. This block then executes and it overwrites the scheduled assignment. So then the value would be 41. If this block executes first, then it schedules 41. But this one comes along and executes second, and it overwrites it, so the value is 43 that it schedules, because we're based on the current of 42. So in this particular case, the results are indeterminate. So the guideline for using non-blocking assignments is to use non-blocking assignments to assign to any register used by other procedural blocks and assign to registers from a single procedural block. So if you're going to use count, if you're going to assign to it in this block, do not assign to it in another block. Okay? As long as you do that and you use non-blocking, then you won't have this problem. So that's very important to do. So non-blocking assignments guarantee race-free simulation, but you must obey these following two guidelines right here in order to do that. Okay, you can also use non-blocking assignments to schedule changes at an arbitrary point in the future. A new value is added to the assignment queue without affecting the previously scheduled assignments, and they replace a previously scheduled assignment at the same time offset. So let's look, here's the syntax. We have target, then our non-blocking assignment, some time delay expression, and then expression. Let's look at an example here. So here we have a blocking assignment, and the rest of these are non-blocking. So this happens immediately. R gets assigned the value of 1. Okay, so that's our current value of R. Then the next one, this is a non-blocking assignment, so it schedules a value of 2 at the, this just means at the current time plus 0. In other words, at the end of the time step, it's going to update to 2. So what does this next statement do? It's going to schedule a value of 3 to be assigned to R at the current time step, the current time plus 10 time units. Similar, this one is going to schedule a value of 4 at 20 time units from now. This one will schedule 5 at 15 time units from now. So these are all scheduled events so far. This one will schedule a value of 6 at 10 time units from now. So these are in a queue, so it would do the 3 and then the 6. So the ultimate result here would be 6 so far. Similar, schedule 7 at the end of the current time step. And what is this statement going to do for me? What is R? Right now R is 1, right? That's the current value, because the rest of these are all scheduled. So this is 5. We're going to schedule a value of 8 to be assigned at 5 time units from now. Now notice there was no delay in any of this execution. These are all scheduled events. So from here all the way down, we haven't lost any time in all of these scheduled events. Okay, so time did not advance between these points. We're still at the current time. So in a previous lecture, here's some examples of time control, which are used to create events. We had just simple delay-based or regular delay. We have intra-assignment delays, like this. Zero-based delays, which are good for when you're doing initialization stuff sometimes. Don't use them really that much. These get used a lot. Then we have event-based, where we have regular events at positive or negative edge of a clock. Named events, which we haven't talked about. Also or control where you have at pause edge clock or neg edge reset or whatever. And we also have level sensitive where you're waiting for something. Okay, all of these timing controls can create events. We can also, just changing a register or a wire, that too can create an event. So I want to look at, we're going to go through this simulation process again, and I've changed it in my example this time so it's a little more color coded and you can kind of see the event queue a little bit better. So this represents all the events that the simulation engine has queued up for the current time. So as we go down, that represents time, and from right to left represents the order in which the simulation engine is going to execute these events. Okay. So we're going to go back through this example again, and before I talk to you about, I called it a pool, like an execution pool, or they're waiting to be executed. I'm going to show you now more in terms of what we call the event queue. I think the actual Verilog language standard calls it the stratified event queue or something like that. I looked at the IEEE spec, and of course each simulation engine may do it slightly different. How it does it is up to the vendor, but as long as they stick to certain guidelines which are specified in the document. So I'm going to take you through this again, and I've color coded it this time. So let's pretend we're the simulation engine now, and we're going to take each of these processes here, procedure blocks, and we're going to queue them up basically to be executed. So we're going to, all these right here, this one's queued up, this initial block, then we have another initial block, I've queued it up, queued this one up, queued this one up, and this one up. Okay, so when we start the initialization, everything is at X's, okay, and these little arrows again are representing where it's going to start, where we're currently at in the execution of each of these blocks. And our time is at 0. So this is time, these are the events queued up for time 0. So we need to execute each of these blocks. That's what these represent. Okay, so the first thing we're going to do, it's going to start through this block, it's going to come down, count's going to get set to 0, foo's going to get set to 0. We reach the end of this block, it's an initial block, so we don't do it anymore. So it goes away and it's no longer in our queue down here now. So the simulation engine can say, we're done with that. So now let's say the simulation engine picks the next block here that we've queued up. Okay, so we're going to start, we're going to go through, we're going to set clock to 0. Remember that causes now, we went from an X to a 0, so that causes a transition. So that transition causes an event. So the simulation engine actually queues these two processes up again. It says, okay, something's going to need to happen because these are things that are happening in the current time step, which is 0 right now. So these two are going to get queued up again, that something needs to happen. Okay, so then we get to this forever, so we keep going down through here, forever at 50. So now this is another, this is a delay which will cause an event. Okay, so now the simulation engine knows that at 50 time units from now, it needs to queue this block up again to execute. So it's going in the event queue for time 50. Okay, so now that block is done for right now, for this event queue, for this time step. So it's gone away now. So now we can go to the next one. So it gets over to here and says, oh, it sees an at neg edge clock. So, okay, so far I don't have that, even though we did queue some stuff up. We'll get to it later. But it knows it can stop right there. Okay, so now that process is done for right now. Okay, now we can go to the next one, this yellow block. And it starts executing down through the code, and it gets right here to this wait. Well, count's not equal to 2 yet. Okay, so we wait with that block. So we're done with that block for right now. Okay, so now we get back over to the purple block, and we get all the way to this at neg edge clock, okay, that's we need to wait. We can't do anything further right now because there was, when these first ones were put in, they just needed to start executing. Now it puts information in there that it knows what it's supposed to do at that time. So basically we've gotten to all these events now for each of these, but now we know we need to execute this event, okay, and it knows that, oh, that was a neg edge clock, so we can continue on here. So now foo can get bumped up to 1, okay, and then after it does that, it comes right back around and it's waiting again, okay, so it can't go any further. So that event is done, it's out of there. So now we're back to the purple one, and we can start executing it because it was put in there for the purpose of doing something at the neg edge of clock. So now count can go ahead and increment, so it increments to 1, and we come back around, we're right here, we're waiting again, so that process is done. So now the only thing left is we go to time. We can increment our time now because all these blocks were sitting there done waiting for something to happen. They couldn't go any further. So now we go on to the next time step, which is 50. So now we can come back and start executing our clock equals the not of clock. Okay, so that changes it from a 0 to a 1. Well, that change in value could cause an event, but in this case there's nothing waiting that would do anything for, so it doesn't create any event in the event queue. Okay, so we do that, we come back around because it's forever loop, and boom, now we're waiting again. Okay, so we queue up that from 50 time units from now, this thing is going to need to execute again. So the event queue for this time now is ready, and this block is sitting here waiting. Okay, so now everything's still waiting, nothing's happened to these others, nothing's caused these others to come back and execute. So now we can advance the time, we're now at 100. And you can see the next thing to do at 100 is we're going to change the clock again. So sure enough, we do that. We change it from a 1 to a 0. But now this 1 to 0 change, this transition on the clock, is going to wake up what? 2 of these neg edge processes. So now these processes are going to get queued that they need to happen during this particular time step. And this is what we want for simulation. Okay. Oops, where was I? Went back. Okay. So those got queued up. So now we've done that. We've looped back around and we're waiting, so that process is done with. So the only 2 processes for the current time right now are these 2 blocks. And so this one starts executing and it bumps foo up to 2. Comes back around, now it's waiting, and we're done with that process, so it went out of the queue, and we pull this process in, and so then it starts going on from where it was, bumps count up to 2. Okay, but now we bump count up to 2. That change in count causes another event to be queued, and that is this event that this thing was waiting for, count equal to 2. So it's going to queue this guy up. This is one way that the simulation engine could do this, but you know, certain vendors may do it slightly different, but this is the idea of what has to happen. So now this process is queued up. We've incremented count. Now we continue on until we get back to the at, and then we have to stop again. Okay, and we take that process out. We're done with that one. Now we execute the next event, which is this yellow block. It goes down and it writes count is 2, writes that on your screen, and then it's going to continue on. It gets to the end, and so this is an always block, so I start over. Okay, there's nothing to stop me. There's no delays or anything in here that's going to stop it. So it says wait until count equals 2. Well, it is 2, so it writes this count is 2 again, and it just does this forever because there is nothing in here that is going to cause another event to happen. And that's why it hangs. So this simulation hangs at this time, and it can never advance. So I wanted to go through this again to give you a better idea. The other thing, too, to mention is when we talked about non-blocking assignments, imagine those if they had been in here in some of this, how they would have been queued up at different times, too. So this is how the simulator goes through this. So in Lab 4.1, I want you to learn the difference between blocking and non-blocking assignments, and learn how non-blocking assignments affect sampling, and learn when assignments are physically performed. So now we're going to talk about wires. Okay, let's say that we had a bus, you know, just like on a circuit board. You got a bus that's got a lot of wires, okay, and maybe you have different drivers, and in this case I've shown A, B, and C drivers. All of these things drive in the bus. I mean, maybe in this case you've got maybe this is a CPU driving the bus here. Maybe this is some chip driving the bus. Maybe this is another chip driving the bus at certain times. So we want to learn how can we model that in Verilog. Okay, so let's say these are our waveforms, and we'll say this is 1, 2, 3 time units 1, 2, 3, and so on. So here's the signals that are coming from the device on A, B, and C, and this is what you would expect if you were on the bus. Okay, so if everybody's driving the bus low, you would expect Y to be low. If somebody was driving the bus high and somebody else was driving it low, you'd expect it to go unknown. Okay, so this is what you would expect for Y given these different conditions, and this means tri-state right here, or high impedance. So let's just try to do it using we'll just use our non-blocking assignments, and we'll use a register Y and see what happens. So let's say we wrote 3 initial blocks, and each of these blocks will describe the waveforms for A, B, and C. So in the case of A, we're going to say, okay, at the current time 0 right here, we're going to schedule a value of 0. And then at time 1, we're going to change it to a high. Then at time 4, we're going to change it to a low. And then at 7, we're going to change it to high impedance. And so we do this for A, B, and C. So now what happens, though, based upon these assignments? So let's look at this time 0 here. Who all's driving at that time? Well, we can see that this one, Y equals 1 tick B0, and here C, it's also doing a 1 tick B0, and for B, it's also doing a 1 tick B0. So whoever is, depending on the order here, whoever's scheduled last is going to set that to Y. Well, that's okay for this time frame, but when we get to this one, let's see, for 1, here we go. This one schedules a 1. This one doesn't do anything, no assignment for that time period. It just does it at time 0, 2, 6, and 9. So here for time 1, this one schedules a 1. This one over here schedules a 1. So they're both going to schedule, or no, I'm sorry, that was time 2. This one doesn't schedule anything. That one schedules a 1. So we're not going to get our X, or our unknown. And also, depending upon the assignment order, Y is going to be whichever the last one was that did the assignment. So we're never going to get our 1 tick BX. So we can't really use this. So registers can't be used to model buses because they take the value of the last assignment. And so the last driver decides the final value. And so there's no X if conflicting values are driven on the bus. You're either going to get a 1 or a 0, whichever was last assigned. So we need some other type of object to handle these buses, and that's where the wire comes in. And so a wire, the final value, is a continuous function of all the drivers. So here's our syntax. We have wire, And then we have a list of names, one or more names. Optionally, it could have a width to it. So here we have wire, just a single bit wire named W. Here we have two wires named A and B. Here we have an 8-bit wire. Here we have a 16-bit wire. And this, of course, is a syntax error. It needs to be done like this. Okay, and so we have two wires here. One's 4-bit and one's 8-bit. So you can have single and multiple bits only. You can't have an unsigned integer value. I mean, they have to be unsigned integer values. It can't be signed. And you'll have the use the MSB on your left and LSB on the right. There's no integer, time, real, or memories for wires. Okay, you can drive wires by using what's called a continuous assignment. Okay, and this is the syntax here. Assign. Wire target equals an expression. Continuous assignment statements continuously drive a wire with the value of an expression. So the final value on the wire is a function of all the continuous assignments on it. So let's see how that works. Also, the place to put these assignment statements is within your module, but not within your procedural blocks. Okay, they can be between your procedural blocks. So here's some examples. Assign W equals 1 tick B1. Assign W depending upon the value of CS, either D or a tri-state value. Or here's one, assign data equals the concatenation of two other values, which could be registers or other wires. And here's a DB1 and DB0, of course, are wires. And this is a concatenation. And so both of these are assigned, the width of this should be equal to the width of that. So this here could be either another wire or it could be a register. But these are wires. So now let's go back to our example and try to model the bus. So here we've written the three initial blocks for A, B, and C. And again, like at time 0, we want A to be to 0. Then at time 1, we want A to go to a 1. And then at time 4, we want it to go low. Time 7, we want it to go tri-state. And then similarly for B and C, we've written the equations. Okay. So now let's see what happens. And here's how we write for the drivers. We say assign x equals A, assign x equal B, and assign x equals C. Okay, so it's going to be a function of all of those. So let's see what happens here. So at time 0, A is driving at low, C is driving at low, and B is driving at low. So x is going to be low. Now at time 1, A is going to drive it high. C is still driving low because we haven't changed it yet. And B is driving still low. Okay? So you will get an unknown because of these conflicts here. Okay? So we get the proper behavior that we want by using wires. You can also include a delay in your continuous assignment expressions, and this is the syntax, and we'll look at that more. So you can also specify different delays for rising, falling, and turn off, which would mean going to a tri-state or high impedance, tick BZ. So in this case, if the simple way is you just have £sign and then a delay, and that's for all transitions, whether it's going high, low, or to high impedance. Or you can specify just a rise and a fall, or you can specify a rise, a fall, and a turn off, high impedance. Okay. So let's look at how these would work for these particular examples that I have here. So if I say assign delay 5, so that 5 is valid for rise, fall, or turn off. and I say W equals 1 tick B0, which delay is used? Well, that one's obvious, 5. That's all there is. What about for this one if I say W equals 1 tick B0? Well, this is for rise and this is for fall. So the value is 7. That's the delay it'll use. For this case, I didn't specify the turnoff delay. So which one is it going to use? It uses the minimum delay for unspecified transitions. So now in this case, I did specify. So it's going to use the 3. In this case, I said BX. I didn't say 1, 0, or Z, so now what's it going to use? Well, it turns out that it uses the minimum delay for transitions to tick BX. Okay? Now here, which delay is it going to use? Because all these bits are different in this bus. Well, it uses the LSB to determine the delay transition. So bear that in mind. And in this case, okay, you might have to think about that one. I'll let you think about that one. Now we're going to look at the continuous assignment again, and it uses what's known as an inertial delay model. And that model says that if the input changes before a previous input value is assigned to the wire, then the pending assignment will be canceled. So what happens in effect is it will reject narrow pulses. So it's similar to a buffer with limited bandwidth. So this is known as the inertial delay model. So let's take a look at this model. So remember, if input changes, the pending assignment is canceled. Here we have a wire W and a register R, and I've said first of all that I'm going to assign W equal R using this delay. So here's an initial statement where we're going to define R. So R starts off at 0, then at 20 time units it goes high, and then at 25 time units it's going to go unknown. Okay, so when this starts to execute, what are the values of R and W? Well, they're both X, but in this case, in initial, this gets set immediately to 0 at simulation time 0. W, however, is going to remain X until we get 10 time units out, and then it's going to assign that value of R, which is 0. So now we go along, and R goes to a 1. So then it's going to schedule, it's going to want to schedule at 30, at how far? 10, 20, at 30, it's going to want to schedule a value going to 1. However, before we ever get there, R changes. So then it reassigns. It has to cancel that pending assignment and reassign again. So now it's going to reassign for 25 plus 10 for it to go to X. If the input is reinforced, the previous assignment makes it through. Okay, this is just basically, let's look here at 20. Okay, so at 20, we come along here, and it assigns a value of 1. That's this right here. Then when we get to 25, it also assigns the same value. So it's not going to cancel the one that was at 20, which was scheduled for 30, because it's the same value. So the one at 20 is just basically reinforced. It makes it on through at 30. Now, continuous assignments can drive with various strengths. Okay, so you can have different strengths for a tick B1 and a tick B0. We're going to talk about that next. And the stronger driver will win over the weaker driver. And conflicting 1 and 0s with the same strength yields an X, and a tick BZ has the weakest strength regardless of strength of the continuous assignment. So here's the syntax for this where we have strength. And let's look at some of these strength values that you can use. These are the values, these are reserved keywords that you can use for strength. Supply 1 and 0, strong 1 and 0, pull 1 and 0, weak 1 and 0, and a high Z. So this is decreasing strength going down. And let's look at some examples here. Here we have a wire, and we have a 4-bit register R, and I've said assign supply 1, comma strong 0, W equals R of 1, assign strong 1, comma pull 0, wire W equals R of 2, and then assign pull 1, comma weak 0, W equals R of 3, and then weak 1 and supply 0, W equals R of 4. So now, if R is equal to this, what will be the value on W according to these strengths and our transitions here? Okay, so I'm going to open this up, see if anybody wants to take a crack at telling me what they think is going to be here. If you got pencils and paper, try and just do it real quick on paper and see if, for this first one, let's just see if we can figure it out. First of all, this is R1 right here. Notice our register was 1 to 4, so this is R of 1 right here. So this is high, right?
Why is that?
Actually, I'm going to let you work these out. I'm going to go through them, but I want you to work them out. We'll come back to them again at the next lecture. I just want to see if you can figure out why. Okay? So I'm going to show you the values. And I want you to go off kind of offline and do these, and then next time we come back and we go through them again. I'm going to put them all up here. Okay. Just keep in mind about the strengths and which ones win. Okay, there are other wire types that are also available. Besides wire, there's try 0, try 1, a wire and, a triand. There's several different ones, but you're mostly going to use the wire. Okay. And there might be cases where you want to use the others, but that's the one you're going to use the most for everything. In most cases, undefined identifiers are implicitly declared as 1-bit wires. So if you don't declare it, it usually will, the compiler will just default and assume it's a 1-bit and automatically do that for you. But the guideline is always declare everything. If it's 1-bit, go ahead and declare it 1-bit. Verilint is just a linting tool that helps you debug. So it'll warn about undeclared wires typically. So in lab 4.2, I want you to learn how wires are used to model buses and learn the difference between assignments and continuous assignments, and to learn the effect of delays and strengths in continuous assignments, and learn the effect of the inertial delay model, and to learn how delays in continuous assignments affect sampling. So and that's all I have for today. So how are we doing on time, Michael? We got about 20 minutes left here.
We have about 20 minutes left.
Okay. So how's everybody doing as far as their simulators that they're using and waveform viewers? Is that going okay?
Okay, everybody should be unmuted now, so you can talk.
Did the event queue, did that make a little more sense this time going through it again?
What I didn't understand was when you have a non-blocking assignment
and
they're scheduled at the same time, who wins?
Whoever did the last assignment. If
So
I understand.
You really don't know.
Well,
it's deterministic.
Well, it's deterministic if you follow those rules that I gave you, those guidelines. If you're going to assign to a register, do it in one procedural block. Don't do it across blocks.
And the other thing I didn't really get was the couple slides back when you were talking about the strengths.
Okay. Which ones? Let's see if I can go back here. Oops. Oh, wrong way. Just a minute. Okay, what now on strengths?
Yeah, why was that? I think it's the next slide down. Why was that first one? I don't care, or I guess it's an unknown.
Yeah, unknown. That's going to have to do with who's driving it, what values are driving it. That I want you to I kind of want you to struggle through right now until we get to the next lecture. I want you to kind of see if you can figure this out. You're gonna have it in the lab, so you're gonna play with this a little bit.
In your strength table, you were showing supply 1 and oh wait, well, okay, I understand why this is that way. Never mind. Supply 1 and supply 0 are the same strength. Is that right?
Supply 1. Oh, let's go back.
And supply 1 and supply 0 are the same strength. Right?
Yes, across. Just one's for a 1 and one's for a 0.
Gotcha.
Okay.
Well, that explains it.
So these are good for modeling different types of things if you're driving buses and things.
Your question about the simulator, I'm still using the Veritag, and it works very well.
Okay, did they have some it looked like they had some pretty good instructions on their website.
Yes, it's been real good. I've been playing with the waveform viewer. I'm still got all the wrinkles worked out of it, but
okay,
it seems to be just about as well as the because the ModelSim thing has to be in an XP. I've got the Veritag on a Vista machine, and then I do your lectures on the XP machine, so I can do it as we're going. Works out nice.
Okay. Now it might be nice. I didn't write any type of tutorial or anything for the Veritag, but if you would like to do that, or somebody would like to do that, maybe make a little short tutorial on how to get it up and going, I could put that on our website stuff.
Well, let me think about it. I'll wait. Thank you. I enjoyed the lecture so far.
Okay. So yeah, let me, I'm going to go back up here for the top. Just remember these two guidelines specifically when you're doing non-blocking assignments, okay? Especially about assigning to a register from a single procedural block. If you don't, your code is going to have big problems, okay, depending on just like in this case. So this is, and I've seen this happen with people that have used Verilog for a while. They'll assign to count one block, and they'll do some other assignment another block, and that's just a big no-no. You're headed for disaster if you do that.
Will you get a warning of any kind, or Verilog? Is there basically any tool that'll warn you that you've done that?
I don't even know if Verilog will do that. I don't know. I don't know of any that'll warn you. Just have to try and see, I guess. But yeah, there's things you can get yourself in trouble with real quick with Verilog because there's not, for some things, there's just no warnings to be given.
How would you assign count from two different sources if that was necessary to do?
That's the point. Don't ever try and make it necessary to do.
All right.
It should not be necessary to do.
So every register has only one source of information, is that right?
Well, you're going to put the assignment for that one register in one procedural block somewhere. Okay. So, and I can't emphasize enough that it's just a big no-no to ever assign it in two different blocks.
That's a little counterintuitive.
How's that?
Well, I don't know. I just seem the way I think that could be a problem for me.
Well, let's think of it this way. I'll give you a clue here. When we write RTL code, this is a real common expression right here. This, say, like @pause edge clock. This would represent like the clock input on your flip-flop. Okay, and then this would actually represent your this block itself would like represent your flip-flop.
Mm-hmm.
So you wouldn't be doing that from two separate flip-flops. It's all done within one flip-flop. I don't know. We'll get to that, I guess, a little later. But anyway, just remember, don't ever do this type of thing. Stay away from this, and otherwise your code is guaranteed to fail. I'll say that.
Just a quick question. Of course, I haven't tried it to put it in real code, but like if I realize in the simulator if I do it, I'll get inconsistent results, and sooner or later I'll realize it's not doing what I want. I guess if I'm lucky and I do the right test. But if I was to put that in my Aussie, for example, if it was something that would fit in there, or if it was appropriate, would it burn up the chips?
No. It'd be. I've never really tried. It'd be interesting to see what the compiler would say on this, something like this. But
I can see where if I had several blocks and a couple of them were trying to make it be high, and another couple try to make it be low with that, a particular output lead, I could maybe blow up a driver, maybe, or is it protected somehow?
no, it's good. The simulator, and it's unknown as to what the simulator will actually turn it into, but it's going to turn it into something, But what it turns it into, it may just throw away one of the blocks and pick the other block. Okay.
So it wouldn't actually hurt it. It just wouldn't do what you wanted when you tried to make it. When you tried to test it out, it wouldn't be working like you thought.
Yeah. Yeah.
You'd get bad garbage in, garbage out. Right?
Yep, it's garbage in, garbage out for this stuff, and I generate a lot of garbage in, believe me, so you know what I'm getting.
Thank you.
Did the stuff I went through, because I changed this my lecture a bit on the event queue stuff. I'm wondering if did that tend to make sense for you this time?
That was helpful.
Okay, I thought, well, maybe if I color code these things and show how they get queued up, that might help a little better.
It did.
Yeah, I think the randomness of this is it helped a lot.
Yeah, the whole thing with the simulator is that you want to be able to simulate everything that's happening at a particular time frame, and so you have to do that with a sequential type CPU to do it. So this is the method it actually kind of goes about doing that.
But the actual assignment, in other words, take what's on the screen, it's apparently smart enough to know that an initial comes before an always. So therefore it queues those up. But I assume the assignment of the two initials is random. Is that correct? And the assignment of the three always is random?
It could be. It's a little, and it shouldn't really. You need when it comes down, you're going to eventually want to write RTL type code. Okay, and when you write RTL code, you're not going to be using any initial blocks. Okay, synthesizable code will have no initial blocks in it. Okay, this is all for simulation purposes, these initial blocks. So, yeah, the exact order, you might want to look at the, I looked last night a little bit again at the IEEE spec for Verilog, and I think what most simulators tend to do is they pick the initials in the order in which they're in the code. But just assume that, I would just assume that when you write them that it may pick either one.
And then the other thing that wasn't quite intuitive is when you got to an always, that changed the clock, so therefore you triggered a negative edge event.
Well, no, when I get in the remember the always block just sits there and it just runs forever in a continuous loop. So I'm running around, I come back up to, let's say I'm coming to the always, I get to this at neg edge clock. So it's then waiting for the event. Something else had to trigger the event.
Okay, so that was the initial where clock went to 0 was actually what triggered the neg edge event earlier in the same time period.
Say that again.
just agreeing with you that, yes, the actual negative edge event in the clock, I guess, was triggered by the light blue initial box.
Yes, it got when the clock first changed, because its clock was initialized to an unknown. That's everything comes up as unknown. Okay, and then when it changed from an unknown to right here in the blue blocks, it changed to a 0. Going from an X to a 0, that's considered a negative edge. That triggered a neg edge event to be queued.
And the neg edge event is something you actually didn't show on the screen. It's kind of like another register somewhere in the simulator.
Well, I showed it in the event queue. Here we can go. Let's try going through this first, just a little bit here. Okay. Let's say, okay, there we go. Those two get set to 0. That process is out of there. Then we come. Then this process right here that we had queued up, it starts to run. So we start going down. We set clock to 0. Okay. So that causes an X to 0, a neg edge transition, and that transition then causes these two processes to basically be put back in the event queue far as that type of an event, a neg edge event. That's what I'm saying here. This event queue is basically recording different types of information of what it needs to do. And if you look in the Verilog spec, it's like a 5-tiered thing. There's quite a few different types of things that it can do. So I'm trying to kind of put it in one line here. So basically these neg edge event information are getting queued back up. Notice I still have a green and a purple block we haven't got to, and that's just to run them the first time to get to the @ symbol. So these two are then queued, and then of course this gets to here, queues the next thing, removes that block out of the, okay, and then this one is just from the initial starting to run. So it goes from here to here and says, okay, wait, we're done. That block's out of there. Okay, then does the yellow block. We'll get past that one. Then we got this initial just running the thing for the first time right here. So we go from here to here, and we're waiting. That's all it can do for now. And then these two were the ones that we queued for the actual neg edge event. So now these guys are actually can wake back up, and they can actually do the neg edge thing and continue running. So the green one's going to start running, doing the neg edge event, incrementing foo, and then looping back around to the @ and then it's just stuck there again waiting. Then that process comes out of the queue, and then this next neg edge event can happen and increment the count and so on. That's what I was hoping I could try and make a little clearer. Now, like I say, the actual simulator, it may do things a little differently than what I showed you here, but in effect, it's going to want to get all the events, anything that's supposed to happen during this current time frame, which was back here at 0, it's going to want to get all of these things in the event queue and process them before we go on to the next time. Okay.
That part of it I understand. If you go back about 2 or 3 slides where you had the 7 events all stacked up.
Okay. Right here? At the beginning? Well, I only got 5 there. This is just, these events stacked up are basically just, okay, start running each of these, okay? Because we've just initialized them and they need to start running. So they're all stacked up, ready to run. And my pointers are at the very beginning of each of these.
Okay, if you'll advance 1.
Okay. Next one.
One more.
Okay, that block went out.
To the point where we can see the second occurrence of the ones that are waiting for neg edge.
Okay. Okay, so clock is getting set to 0, and that's causing an X to 0 transition, a neg edge transition. So the simulation knows that, hey, I've got 2 blocks here that are sensitive to that. Okay, so those are going to get queued up.
Okay, I guess the question is, as we were advancing from right to left in the event queue, the neg edge event has occurred as you
it has
the blue,
yeah
and yet the first occurrence of purple and green cannot see it.
well that
So,
event, as far as processing that event, the neg edge, it hasn't got to that in the queue yet. Okay, and first they got to start running before you can. I mean, you're sitting here at the beginning of these things. It hasn't even gotten over to that part of the code yet. Okay, so all I'm saying that this is doing is just scheduling in the event queue. We need to process 2 neg edge clocks here for these 2 blocks.
So you're saying that something else was confusing me. It's the clock and the time. That, in other words, if I'm on clock 1, that doesn't mean I'm on time 1 necessarily. Or is that going to always be the case in these simulations?
The clock is just a register that we're changing the value of at certain times during our simulation.
Okay, that's what I was thinking. In other words, the simulation, when you've achieved all of the events in your simulation that you have defined up front at your initialization, and it's at the time it's ready to go, it gets to the point where it's going to lock and it needs to go on to the next, like 50 or 100, then the time increments. It's not necessarily tied to that clock register.
Right.
But,
Yeah, all that.
whoever calls it, it's not 5 clocks doesn't mean anything unless the code asks that to go to 5.
Yeah.
Right?
Yeah, it's when you've processed everything in the event queue, all your blocks are sitting there. They can't go any further until you advance the time.
Right. It's satisfied except for the time.
Yeah, and then when you advance the time, then you start processing the events in the queue for that time. Okay, and as you process those events, you may get other events for the same time period.
Right.
So, and if you kind of look at this and think of this, you've got, let's say you've got this clock you want to run, and at neg edge clock, you basically, these are happening during the same time. You want these both to simulate as though they both happened at the same time.
Yeah. In fact, the way you redid it, that made it clear to me that was happening. Before, I was trying to figure out how they did that in time, I was tied up with the precedence of the order. In fact, one of my questions was, if you got a module and if you try to do something, but I kept getting in the loop where I was not thinking. I was thinking it had to go to another time. I was looking at it like each of those events was incrementing the time, and this made it clear that it's not, and that's why I was getting confused.
Yeah, and see, and the problem with this block here is there's nothing in here once it hits this weight that's going to ever stop it from running, because it's always, remember, these always blocks, they just keep running until there's some event that happens, or something that blocks it, that it has to wait a time delay or something like to that effect. It will not get out of that block, processing that block.
When you introduced that loop that it got itself into, I thought to myself, okay, what you can do is set count to something other than 2, but that that's exactly what you told us not to do. So how would you fix that?
Well, in this case, maybe when you hit 2, you might want to actually put a finish. You may want to that's the end of your code. But if you're not wanting it to finish, you're wanting it to, the rest of the code to continue running, you might put a delay in here. It might. I don't know if you want it to write count every time anyway. It kind of depends on what you want to do, but the whole thing is there's nothing in here once it hits that count equal to 2 to cause it. I mean, you could put a wait count equals 500 or something after this write statement, or wait until
Oh, okay.
count equals 500 or whatever, or some other value, so that the rest of the simulation can continue to run. Because by putting another weight, in here, that's going to allow the simulation engine to go on with other processes.
Okay, that makes sense. One other question. Count, the C and T for count and CLK for clock makes perfect sense to me, but what in the world does foo mean? Anything?
No, it's just a silly word.
Okay.
Just to register some variable.
Okay, you could have called it goo or who.
Yeah.
I should have put bar in there.
I'll put foo bar
So
or
yeah, it's
bar.
either foo or bar are your two choices.
So in real life,
So
let's.
you can keep scheduling events if you if you had one of those processes that said look at the negative edge of clock and then clock changed to positive and then negative edge again. You can get in a loop that way too.
I'm not sure I followed that one, but yeah, there's a lot of ways you can get into loops
Yeah,
if you're not careful.
Yeah, it seems like it. What I was saying is that if there was a process that went from positive edge to negative edge in the same time step, and then went back to the negative edge, then kind of you could get this toggling in the same period in the same time step. It's not in here, but if you had something like that, it would.
Yeah, but usually to make that positive negative edge for a clock, I mean you're changing it every so often, so there is something.
Yeah, that's what's driving is that block there.
Yeah. Yeah, I've been trying to think how to. This part of it's you have to get your head around this stuff. When I first took Verilog, this wasn't explained very well to me, and so I'm trying to figure out how to make it easier to understand to other people.
This count only applies to the simulation, doesn't it? I mean, the clock. In a real system, you wouldn't have something called a clock in there.
Oh, and in your real RTL, your code that you're going to use to generate real logic, you're going to want to run clocks typically, because if you're going to use flip-flops, unless it's all combinatorial and OR gate type stuff, you're going to have clocks coming in. I mean, you're not all this statement here, this initial statement is if you're writing a simulation and you want to simulate, you've got a little clock oscillator and this is what it's doing, every 50 time units. Now these 50 time units, maybe they're nanoseconds or picoseconds or whatever, you can define what that is. But you want to simulate a little oscillator, this is how you could do it. And then this clock may go into one of the pins, let's say, of a module that actually, is your real RTL code that you're going to synthesize, and you're going to have statements like this in your RTL code a lot if you're using flip-flops. Okay, except
I feel better now.
Except in the case you're not going to be using these. You're not typically, if you're going to write a flip-flop, you're going to be using the non-blocking assignment. You're not going to be using this. So if you had this as a non-blocking count with a less than equal here, equal count plus 1, you could write this would physically turn into a counter running on a clock with using flip-flops. But
Say, Kirk.
yes.
Yeah. In trying to explain this this scenario, I was trying to think how you might make that, how you might remove some of the confusion that sometimes occurs here, and it occurs to me that if you stress that time is 0, then real time is frozen, and the simulator is kind of running around in some other dimension while time is frozen doing these other steps, and real time is actually halted during this until all these steps are taken care of. Then real time is turned on again.
Yeah, that's what I was trying to show with this. But yeah, maybe I need to emphasize that more. Is this simulation time? You know, you're doing all these events in the queue during this time until they're all taken care of, and they're all at the same time. Simulation time, or
Right.
real time, I guess, if you want to call it that.
Right.
But there's still another time dimension here, because once again the negative clock was created by the first execution of the blue, and then green and purple couldn't see it until they repeat it again, and then they can see it. So they're actually in this nomenclature, the negative clock really wasn't visible until you started the subsequently stacked event queues.
Okay, but
and I guess that's kind of what I was struggling with. It
but
seemed if there's a flag and you can see it, but actually you could the blue and the purple could not see that flag until they got to their second execution.
yeah, but the thing to keep in mind here is this time, because and basically it's making all the simulator engine's making all these calculations for everything, but then when it puts it out, whatever it finally winds up at, it's going to be at time 0. It's going to put that out.
Yeah, I understand that part.
Okay. Just how it does it is always the trick. But it has to do it in such a way that, you know, it gets all of these events, all these you have to keep in mind this is all parallel events, and it has to, you know, calculate those for that particular time step that you're on. I call this time step.
But
'Cause
if I'm understand it right, what you're doing though is you're having. Let's take a real example, like Ozzy or Janice, to do a simulation to exercise the code that you're going to write, or the code that was written. You've got to, every input lead on that device, you've got to, if it's a clock, whether it's a crystal clock or phase lock, whatever it is, you've got to you got to write carefully, and then in this simulation, these are the sources to that card, and if they don't mimic the real world, of course, the results won't mimic either, right?
yes, definitely. So, like, here, let's see. I could get out of this for a second, and oh no, don't tell me oh, there we go. I thought my computer locked up for a second there. Let's go into ModelSim. Okay, like this is a version of Ozzy Janus that I'm working on. So here's the top level of Ozzy Janus for what I'm doing, and I have another module I wrote called Sim, and this happens to be the very top level of everything. So if you come down through, and this module is written purely to drive the Ozzy Janus and all the other all the other Verilog files that are attached to it. So in here you'll see I have wires like these, flag A, B, and C. These are wires that are coming from the USB chip to the FPGA. They're going between the two parts. And further down I have some initialization stuff that I do, because remember, when the simulator comes up, everything is unknown, okay? However, in real life, in the FPGA, it will typically set all your registers to 0, okay, after a reset. But in simulation, it's not going to do that. So if you need one to be at 0, you need to go in and set it to 0. You know, and then in this I call this behavioral code, because this is, you can't synthesize this. This is good for simulation, but I can do things as far as testing conditions, writing out things if if I believe there was a problem. Delaying for a certain amount of time before I check something else. And then I can get on down here. Let's say I go on down, and here's the actual Aussie instantiation for the module. And one of the things here is it has this IF clock. Well, okay, I need to drive that because on the real FPGA there's something driving that signal. So in my simulation, down here in the bottom somewhere, I have an IF clock. So here's an initial, and I just put a little display that the clock, I've started the clock just so it's in my comments as it starts to simulate. I start off by setting it to 0, and I delay some random time here just for fun. Then I have a forever loop, and I set it high, I set it low, and I do this forever. And the delay, see, I've created this thing called a parameter, which you'll learn about, and I've set the value to 10.4. So it delays 10.4 nanoseconds, sets the clock high, delays another 10.4 nanoseconds, sets it low, and then repeats this forever. Now what I could do if I didn't want a 50-50 duty cycle, I could make this value and this value different. And sometimes I've done that. So anyway, this is just driving that particular clock input. Now there's other clocks in there too, like here's another one. Okay. And in some cases I might have clocks that are the same speed, but I put in a different initial delay just so that they're not exactly aligned at the same time in the simulation, just to see if that causes any problems or not. And then the rest of this code is just actually exercising the part I go through. Let's see here. I actually generate some data. So I start off and I do some delay. I wait till I get to a certain point where I know things are ready to go. And then this is just a for loop here. I wait for the negative edge of the CLR clock. Okay. And then I want it to put out some, I want it to send some data. So this right here is a task. That's this task right here, TLV data. And here I simulate, I wait for the CB clock to go high, then I wait for it to go low, okay, and then I actually start putting data out on two of the signals, and these signals are signals that are coming into the Aussie FPGA. Okay, and so this is 16-bit data here that I put out based on the CB clock. Okay, so this is purely for simulation purposes. This is not something you could synthesize. Okay, the synthesizable code is quite a bit different. It's a subset, and you use only certain things. So like if I were to go into Aussie, and let's see if I can find something interesting. Okay, so here we have an always at pause edge of the IF clock. Now everything inside of this block is all synthesizable. It turns into actual flip-flops. Okay, and you'll notice that for all of this I'm using non-blocking assignments. Okay. Typically, and you're going to want to use, like in this case I said, if I have a reset, then I want to set this particular state machine set of registers, and this is, let's see how many bits wide this 80 state is here. It's 4 bits wide, so I've made a state machine. We can talk about that someday. I don't know if anybody wants to hear about that right now, but anyway, this all turns into real flip-flops. So in this case, let's take this. This is how I would write a particular. Anybody want to see about how you would do a state machine?
Sure.
Okay. So typically I'll say if and this is all inside of a at pause edge some clock, okay, because it's going to be these are going to turn into flip-flops. These AD state. There's four bits here in this AD state. So I say if reset, I want to set it to go to idle state. Now, the nice thing is, instead of just using numbers all the time, and we're going to get to this, you can use things called parameters and local parameters, local param. And so here I've defined AD idle, the idle state, to be 0, and I've defined values for all these other states. So I can use names now instead of using just numbers. It makes a lot more sense. So the key here is for advancing the state, if it's not in reset, then I'm going to, on every clock edge, I'm going to set my AD state, my new state, to this variable, which I call AD state next, the next state that it should be in. This here is just merely a delay for simulation purposes. The actual synthesis will ignore this delay, and I'll talk more about this delay thing sometime, why you would put it in. You don't have to put it in, but for simulation purposes it's very nice to put in. So anyway, I'm going to set the flip-flop, the next state, equal to this variable. Now this variable, I put in another always block, and this variable is a register, and I said always at star, and that means the star basically means that any of these variables that change in here, that way I don't have to write a whole list of them in here because I've got a lot of them that are in here. So it's a short-term notation that works really nice, and we'll talk about that sometime. So here I can define, we haven't talked about case statements yet, have we or not?
No.
Okay, anyway, you have case statements in Verilog, and so based upon my current state, I can choose, let's say that I'm in the idle state. It chooses this one. I think we did, I can't remember, but anyway.
Yeah, you mentioned that. You did. You're right.
Yeah. So this particular always blocks. I don't use any non-blocking. These are all blocking statements. This turns into pure combinatorial type logic, just ands and NAND, AND gates, OR gates. And so I have code written here for each of the states. Like here's a state, here's a state, and so I want to determine my next state. So like if I'm in an idle state, and if I have a reset or this particular timer hasn't gotten up to a certain point here, I just stay in the idle state. So I set my AD next state equal to idle. Otherwise, I go to AD wait low. Okay, and I have some other variables in here that I'm setting for certain things too as we go along from state to state. So when I get to this state, I wait now until this particular signal goes low, or wait until it goes high. So I stay in this state, is what I'm telling it, until LR clock goes high. Then I'll advance to the next state, which is AD wait high. So anyway, this is all what we call just a state machine. And all the logic for this variable right here is all just AND and OR gates. Basically, it reduces this whole big always block down to AND and OR. And then that variable gets used right here and clocks it into AD state, which is an actual flip-flop, which holds the value from clock to clock. So go ahead. Let's see if there's anything else interesting. We talked about functions. Here's a function I use in here just for making calculations. I'll talk about this sometime. This is an interesting little function. Basically, it, let's see if let me find it. I'll show you something here. Okay, here I've defined this thing called a local param and RF size here. That's my receive FIFO size. And I said that it's, and this is a function, the C log B2, base 2. So I feed it a number. Let's say that I defined RX FIFO size as 2048. Okay. And so 2048 would be the size of the FIFO. So in other words, the FIFO goes from 0 to 2047. So that's why I subtract 1. So 2047 would be the highest value there. Then if this function will actually tell me how many bits that particular number, 2047, needs in order to contain it. And so then I can use that value right here to define how many bits wide this register is. Okay, and that way if later on I change the size of the FIFO, the sizes of these will update for me too. So it's sort of a fun thing you can do. So instead of just using an absolute number here, like, you know, this thing is 16 or 4, you know, I can change my code to try different scenarios, and then this will just update the size that I need in order to hold a value from 0 to 2047. Because I don't need a 16-bit wide. What do I need for 2047? How many bits is that? Start. I'm lazy. See, I got a calculator here somewhere. Okay, decimal. 2047. And we'll turn that into binary. So how many bits we got there? 4, 6, 11 bits, right? Okay. So if this was 2048, then 2048 minus 1 is 2047. This function would then calculate that, okay, it needs 11 bits to hold that value of 2047. And so then I have, this is equal to 11. So then for 11 bits, I'd go from 0 to 10, which would be this minus 1. Does that make sense? So, but now in the case of like this FIFO data, it's always 16 bits wide for now. I mean, you could make it variable too if you wanted to, but so basically the C-log B2 function, all it does is it takes the value that you send it, and it keeps shifting it right until the value becomes 0, and so it just counts. And so that tells it how many times you go through the loop until you get to 0s, how many bits is in there. So it's just the function is just a compile time thing. It's not synthesizable. It's just a compile time thing. Okay. Any other questions?
When you did the code you did you start from scratch, or did you just redo what was there?
I'm taking what Phil had and basically going from there. Some of it's new, especially what I'm doing right now is quite new.
The Phil you mentioned, is that Phil H or Phil C?
Oh, Phil Harmon.
Okay.
Yeah. So, and some of the stuff in Mercury, I've made some changes in Mercury and Penelope that you're currently using right now. But there's some things that we want to get away from that's in some of the FPGAs right now. And those have to do with metastability issues and clock domain crossing issues.
That's cool. It's it's nice to have this actually related to something real rather than just simulation.
What was that?
It's nice to see where this is actually being used rather than just always being a simulation and not knowing exactly how it was going to work in the real world.
Yeah. So I want you to know you need to know the whole Verilog language so that you can do your simulation. You can write. You could start off writing a behavioral model for specific FPGA just so you could get simulation kind of up and going and seeing that it's doing the type of things that you want. And then you can replace that behavioral model with a real RTL model. And then in my case, a lot of times I'll just write the RTL model itself directly, and then I write all this simulation stuff to go around it, and that's how I exercise it and see, well, what's it doing at certain time points or when I feed it certain things, and otherwise you could never figure it out.
Well, actually, to go to hardware, doesn't Quarta just take these .v files and it will assign what goes in the FPGA? Is that not right?
Yeah, like this Aussie Janus, this is all RTL code. So everything that's in here, everything I have in here will synthesize. And then it'll create a file and that'll just go right in the FPGA. So all of this logic then goes right in there. Okay. But then this sim.v, this is just for me, and my purpose is to debug it before I actually put it in the FPGA so I can exercise it and see that it's doing what I want it to do. So that's where you need the whole Verilog languages to write this, so you can write your simulations and behavioral type models. Because without this simulation right here even, this particular piece of simulation goes through quite a bit of stuff, data moving, and without it, you couldn't find your bugs. That's how we found several in the last several weeks here. So the problem with writing one person writing the code, the RTL type code that you're going to synthesize, and the same person writing the simulation is if you assumed one thing when you wrote the RTL code, that thing was going to work a certain way, you're probably going to assume that when you write the simulation, and okay, it works the way you thought it works, but that doesn't mean it's going to work the way it should work. So it's better to have a second person actually doing the simulation, and instead of the same person doing it. But I don't always get that luxury.
I know that Phil has been very flattering of the work you're doing to help him out and to help us all out. It's for HPDSR. We really appreciate it because he said you've really done wonders with his code.
Well, I'm still learning a lot about this too. Right now, my biggest difficulty in this code right here is I'm having trouble with the USB. That's my biggest problem right now. There's something I'm missing. I'm not understanding right now because I've got a lot of stuff. I'm trying to change. Basically, I'm trying to change the this new code is all going to work basically off of the IF clock. Before it was using other clocks and data going from one clock domain into another clock domain. It might be working right now, but there's timings that can't be guaranteed, and so I'm trying to eliminate those type of problems basically. And we also want to get away from there's a lot of clocks running on the Atlas bus right now back and forth between boards, and that's why you're having this order dependence problem, is due to those clocks. And so I'm trying to actually eliminate those clocks and do things differently so that we won't have this board order dependence. But it's taken me a while. I'm still learning. And there's something I haven't figured out, and that's what I've been battling with here the last several days, is this USB chip. I can't get reliable transfers in my new code that I've been doing. I keep getting FIFO overflows on the transmit FIFO. Simulation doesn't show it, but there's another feature that when you're using the Quartus tool, they have this thing called signal tap, and signal tap allows you to actually capture signals inside the FPGA, and then you can look at them. You can set trigger points just like you would if you had a real logic analyzer or scope, and you can capture a bunch of signals, and then you can see what's really going on with these signals inside the FPGA. And sometimes you might see, oh, hey, something's different than what I simulated. You know, I assumed something wrong in my simulation. So it's a nice little feature. Xilinx has the same thing, and they call it chip scope. And I'll have to show you that sometime too.